Everyone, I'm Lee from UC San Diego. Today, I'm going to present our work on group learning. Machine learning is being rapidly adopted everywhere, such as data analytics and online recognition systems. Engineers and scientists start to apply ML in their daily work. For example, a data scientist at New York Times will leverage ML techniques to determine whether users would click the banner ad or not. She gets ads responses from users in different countries using different platforms. She might be thinking that users in Canada using Android phones might be more likely to click. So she trains separate ML model for each subgroup to predict the click-through rate. We call this practice of building separate models for each separate subgroups learning over groups. So how to do learning over groups in a distributed setting? Essentially, it is a twofold process. First, to materialize and load data to workers, and then schedule ML tasks accordingly. There are two existing approaches to schedule ML workloads. One is called data-parallelism, in which you shard each group evenly to each worker and communicate among workers to synchronize results. However, the synchronization might cause loss of network communication, especially for HTTP-based algorithms. There, synchronization is required for every mini batch. Another approach is called task-parallelism, where you spawn training for each group independently on a worker. And workers do not talk to each other. But due to imbalanced task assignments and training times on workers, task-parallelism often results in idle times. During ML model building, model selection is typically inevitable to control underfitting versus overfitting. For example, the data scientist wants to train a simple MLP to predict the CTR, but she has several parameters to choose from, such as learning rate, hidden layer size, and activation, etc. One configuration of these parameters might work the best for one group, but not another. So she will need to perform a research to train multiple models on all hyperparameter configurations and pick the best model for each group. This leads to many more models to train in total. Recent work in the DB literature proposed a hybrid of task and data parallelism for HDD workloads, called model hopper parallelism. Their idea is to shard one dataset evenly and parallelize model selection. Here is an example. 3 workers each get a shard. Mob first trains model 1 on worker 1, model 2 on worker 2, and model 3 on worker 3. Then it hops models to different workers to continue training on different shards until one model has been trained on all shards. Their approach improves resource efficiency by parallelizing model selection. But essentially, MOP is akin to DP in sharding datasets across all workers, which will not scale well with groups. It might be overkill for small groups, which should be better not sharded. The group scalability problem leads to our work. We wanted to parallelize learning over groups for a wide range of models. To recap, most ML tools support task and data parallelism and a wide range of models such as GLM, GPT, and deep learning, but they prefer model selection and learning over groups sequentially. MOP parallelizes model selection, but is restricted to HTTP-based workloads, mostly deep learning. Our work, Kingpin, can parallelize both model selection and learning over groups. We also support a wide range of commonly used ML models. So this is the outline of my talk. I just covered the motivation and background. Now let me introduce our approach and system Kingpin. The basic idea of our approach is simple. We still want to shard all data evenly as in data parallelism, while minimizing communication costs as in task parallelism. For ETL, we adopt and adapt an algorithm called wraparound from the operation research literature. This ensures each worker gets similar amount of training data and thus similar ML work. Scheduling is tied to data placement. Most small groups are trained in a task-parallel manner. Large groups get sharded across workers. For such groups, we use a novel form of parallel ML execution we call Gradient Accumulation Parallelism, or GAP, to reduce communication costs further. We adopt an extensible architecture that can talk to multiple ML tools. The system is built on top of RAY, which parallels the workloads on physical machines. For ML training, Kingpin essentially acts as an abstraction, enveloping popular ML tools without modifying their internal code. Currently, we support PyTorch and LightGBM. Now we show an example of gradient accumulation parallelism in one iteration. Here is a basic setup. We want to train a simple logic regression. There are three groups, A, B, and C, three workers, W1, W2, and W3, two hyperparameter configs, alpha and beta. This makes it 6 models to train total. The very first step of Kingpin is to load data to workers based on the wraparound algorithm. At the same time, each worker can initialize models. The superscript means the model at a specific iteration, and the subscript means group and hyperparameter config. After data is loaded, each worker starts to accumulate gradients for groups on their charts. If a group is sharded across multiple workers, workers will send the gradient to one leader worker asynchronously. The leader is decided by our scheduler. With gradient and models, workers now update the models. For worker 3, some of its gradients are sent from worker 2. Finally, worker 3 will send the updated models for group C back to worker 2. By then, all workers will have updated models for another iteration. In the paper, we have detailed analysis of existing approaches as well as support for other ML algorithms. Please feel free to check them out. Lastly, we briefly present our experiments and results. For the experiment, we use two real-world datasets, Cre2 and CityExpress. Cre2 is a tabular dataset with many group attributes. We pick country and partner with 18 and 280 groups respectively. CityExpress is an image dataset with 44 groups. We pre-processed all datasets as per standard ML practice and partitioned them into small files for parallel data loading. We conduct the experiments on Cloud Lab. The experiments are carried out in 4-node CPU and GPU clusters. Here are the software and hardware setup. For the experiment, we wanted to know how do the runtimes of ML algorithms on real data in Kingpin compare with the alternatives. We look at two key metrics, end-to-end runtime and resource utilization. We run 3 ML workloads, logic regression, GBDT, and UNet for 12 hyperparameter configurations. We train all models for 10 complete iterations and perform post-hoc analysis. We have 3 baselines, data-parallelism, DP, group task-parallelism, GTP, model task-parallelism, MTP. DP is achieved through all reduced. GTP and MTP are variants of task-parallelism. GTP places entire model selection of a given group on one worker. MTP breaks apart the model selection of a group to place one config at a time. Here is the end-to-end result. For logic regression, Kingpin has comparable runtimes on Cre2 country and partner, despite partner has much more groups. Other approaches are much lower than Kingpin for various reasons. GTP suffers from idle time, MTP has worse I/O time, and DP has lots of communication overheads. For GBDT and UNet, we see Kingpin is significantly faster than the baseline in most cases, while matching the best baseline in some cases. Now we take a closer look at the CPU utilization. On the y-axis is the average CPU percentage per worker. X-axis is the time in minutes. Kingpin can make full use of CPU while having some for-ops after each iteration. In comparison, for-ops happen much more often for DP, where synchronization happens at a fine granularity. GTP has idle time towards the end because of imbalanced scheduling. In the paper, there are more drill-down results as well as scalability experiments. Please feel free to check them out. In summary, in this work, we propose a group and abstraction for ML model selection. We put forth a novel hybrid approach we called group learning that avoids redundancy in communications and I/O. Our prototype system Kingpin shows performance that matches all its 4x to 14x faster than the state-of-the-art ML systems. Last but not the least, We would like to thank NSF, NIH, VMware, and UCID for supporting this work. Thank you.